Welcome to RenEnergy.com, your renewable energy and sustainability platform. Welcome to another technical deep dive from RenEnergy.com. Today, we're exploring the intricate synergy between green hydrogen and proton exchange membrane, PEM, fuel cells, a critical combination that holds immense promise for a sustainable energy future. With the mounting urgency to reduce carbon emissions and transition to renewable energy sources, the importance of effective energy storage and conversion systems cannot be overstated. In this feature, we'll delve into the key materials like perfluorosulfonic acid, PFSA, ionomers and their role in making PEM fuel cells more efficient, durable, and adaptable. From the scientific principles to market landscapes and case studies, we will provide a comprehensive guide to understanding how green hydrogen and PEM fuel cells are revolutionizing renewable energy applications. Scope and importance of green hydrogen and PEM fuel cells. In recent years, the focus on renewable energy sources has intensified as the world grapples with the impending consequences of climate change. Two key players in this landscape are green hydrogen and proton exchange membrane, PEM, fuel cells. These technologies hold the promise of transforming our energy systems by providing a more sustainable, efficient, and cleaner way to generate electricity. Green hydrogen, produced using renewable energy resources, serves as an eco-friendly alternative to fossil fuels and offers a wide range of applications from industrial processes to energy storage. PEM fuel cells, which efficiently convert hydrogen into electricity, provide a vital technology for realizing the full potential of green hydrogen. Together, green hydrogen and PEM fuel cells can revolutionize sectors like transportation, power generation, and industrial applications, aligning with global initiatives to achieve a net zero carbon future. Objective of the technical deep dive. This video aims to go beyond the surface level discussions commonly found in mainstream media to provide a technical deep dive into the inner workings, challenges, and future prospects of green hydrogen and PEM fuel cells. We will delve into the specifics of material science, engineering design, and operational challenges, with a special focus on technical aspects like perfluorosulfonic acid, PFSA, ionomers, electrochemical kinetics, and computational fluid dynamics. By combining a high-level overview with detailed technical analyses, this document seeks to serve as a comprehensive resource for researchers, engineers, policymakers, and anyone interested in gaining an in-depth understanding of these transformative technologies. Whether you're new to the topic or looking to expand your existing knowledge, this technical deep dive offers a nuanced exploration of how green hydrogen and PEM fuel cells are reshaping the renewable energy landscape. Green hydrogen, the building block. Electrolysis methods, PEM, alkaline, and solid oxide. Green hydrogen is produced using electrolysis, a process that splits water into hydrogen and oxygen using electricity. The source of electricity is crucial in determining how green the hydrogen is. Renewable energy sources like solar, wind, and hydroelectric power are ideal for truly green hydrogen production. There are mainly three types of electrolysis methods. PEM, proton exchange membrane, electrolysis, utilizes a solid polymer electrolyte to separate water. Known for its high efficiency and quick response time to changes in electricity supply but is generally more expensive. Alkaline electrolysis, the oldest and most common method, it employs an alkaline solution as an electrolyte. Although generally less expensive, it is less efficient and slower to respond to electricity supply changes compared to PEM electrolysis. Solid oxide electrolysis operates at high temperatures using a ceramic, solid oxide to split water. It can also accept steam, providing more flexibility but requiring high operating temperatures. Purity and storage considerations. Green hydrogen production has stringent purity requirements, particularly when the hydrogen is intended for use in sensitive applications like fuel cells. Impurities such as carbon monoxide or sulfur can poison the catalysts used in PEM fuel cells, making purity a critical consideration. Storage of green hydrogen also presents challenges. Hydrogen has a low energy density by volume, meaning that it requires either compression, liquefaction, or chemical bonding for efficient storage. Each method has its trade-offs in terms of energy efficiency and cost. Hydrogen transportation. Transporting hydrogen is not as straightforward as other fuels due to its low density and reactivity. It can be moved through pipelines, although these pipelines must be constructed of materials that hydrogen will not embrittle. Tanker trucks carrying compressed or liquefied hydrogen are another option, as are specialized ships for larger quantities. Novel methods like hydrogenation of organic compounds, liquid organic hydrogen carriers or low HCs, are under research as potential ways to facilitate easier hydrogen transport. Fundamentals of PEM fuel cells. Electrochemical principles. Proton exchange membrane, PEM, fuel cells operate on basic electrochemical principles to convert chemical energy into electrical energy. At the core of the PEM fuel cell is the membrane electrode assembly, MEA, which consists of an anode, a cathode, and an electrolyte membrane, often made from perfluorosulfonic acid, PFSA, ionomers. The anode is responsible for the oxidation of hydrogen gas, resulting in the release of protons, H+, and electrons, E. The protons move through the ion-conductive electrolyte membrane to the cathode, while the electrons travel through an external circuit, providing electrical energy. At the cathode, oxygen molecules from the air undergo reduction, combining with the protons and electrons to form water. Thermodynamics and kinetics. Thermodynamics. The thermodynamic potential of a PEM fuel cell is determined by the Gibbs free energy change of the reaction. For the hydrogen-oxygen system, the theoretical maximum voltage, also known as the Nernst potential, can be calculated. However, practical cells operate below this limit due to losses like activation over potential, ohmic losses, and concentration losses. Kinetics. The rate at which the electrochemical reactions occur at the electrodes is governed by kinetics. Kinetic limitations often result in the need for catalysts, typically made from platinum or platinum group metals, to accelerate the reactions at the anode and cathode. Over time, the performance of these catalysts can degrade, impacting the overall efficiency of the fuel cell. Understanding the thermodynamics and kinetics of the reactions occurring within a PEM fuel cell is crucial for optimizing its performance. These principles inform decisions on material choices, operating conditions, and design features, ultimately influencing the cell's efficiency, longevity, and commercial viability. Materials science in PEM fuel cells. Perfluorosulfonic acid, PFSA, ionomers. PFSA ionomers, such as aquavion and naphthione, serve as the electrolyte in the membrane electrode assembly, MEA, of PEM fuel cells. These specialized polymers provide high proton conductivity while maintaining excellent chemical stability and impermeability to gases like hydrogen and oxygen. The choice of PFSA ionomer and its thickness can significantly influence the fuel cell's performance, including its efficiency, durability, and operating temperature range. Electrode materials and catalysts. The electrodes in a PEM fuel cell are typically composed of a porous layer of carbon black mixed with a catalyst, usually platinum or a platinum group metal. The catalyst accelerates the electrochemical reactions at both the anode and cathode, reducing the activation energy needed for these reactions. Researchers are also exploring non-platinum catalysts to reduce costs and improve performance. Gas diffusion layers. The gas diffusion layer, GDL, plays a crucial role in supplying reactant gases to the catalyst layer and removing product water. It is usually made of carbon fiber paper or cloth and is treated to be both hydrophobic and conductive. The GDL must balance conflicting requirements of gas permeability and electrical conductivity, making material choice and design critical. Bipolar plates, material and coatings. Bipolar plates are used to connect individual cells in a fuel cell stack, carrying current from one cell to the next and providing channels for gas flow. These plates can be made from various materials, such as graphite, composites, or metal alloys. Coatings are often applied to these materials to reduce corrosion and improve electrical conductivity. Each of these components, PFSA ionomers, electrode materials, gas diffusion layers, and bipolar plates, has unique material requirements that must be carefully balanced to optimize a PEM fuel cell's overall performance and durability. Advancements in materials science are continually driving innovations that are making these cells more efficient, cost-effective, and scalable for a range of applications. Technical role of green hydrogen in PEM cells. Hydrogen purity requirements. The purity of hydrogen used in PEM cells is critical for their optimal operation and longevity. Green hydrogen produced via electrolysis methods like PEM or alkaline electrolysis generally meets high purity standards. Impurities such as sulfur, carbon monoxide, or even moisture can severely degrade the catalyst and reduce the fuel cell's efficiency. Therefore, filtering and purification steps may be necessary when using green hydrogen in PEM fuel cells to meet the stringent purity requirements. Impact on electrode and catalyst degradation. The quality of the hydrogen feedstock has a direct impact on the rate of electrode and catalyst degradation. Green hydrogen, being a clean source, usually minimizes these effects, provided it meets the requisite purity standards. Impurities can poison the catalyst over time, causing a decline in cell performance and shortening its lifespan. By using high-purity green hydrogen, the fuel cell system can maintain high efficiency and long-term stability. Efficiency metrics: voltage, current density. The efficiency of a PEM fuel cell running on green hydrogen can be gauged using several key metrics, including cell voltage and current density. Cell voltage. Under ideal conditions, the theoretical cell voltage for a hydrogen-oxygen PEM fuel cell is about 1.23 volts. However, this voltage decreases with the cell's operation due to overpotentials and other losses. Monitoring the cell voltage provides a measure of the thermodynamic efficiency of the fuel cell. Current density. This metric is used to quantify the rate at which hydrogen is consumed and power is produced in the fuel cell. Higher current densities usually mean higher power outputs but can also result in quicker catalyst degradation and lower efficiency due to higher overpotentials. Understanding the role of green hydrogen in influencing these efficiency metrics is vital for system optimization. By focusing on purity, degradation rates, and efficiency metrics, one can significantly improve the commercial viability and reliability of PEM fuel cells powered by green hydrogen. Design and modeling. Computational fluid dynamics, CFD, models. CFD models are indispensable tools in the design and optimization of PEM fuel cells. These models simulate the flow of reactant gases through the fuel cell stack, predicting performance variables like pressure drop, flow velocity, and concentration gradients. Advanced CFD models can also simulate the electrochemical reactions taking place in the catalyst layers, providing a comprehensive picture of the fuel cell's performance under different operating conditions. Heat and mass transfer considerations. Maintaining optimal temperature and humidity levels inside the fuel cell is critical for ensuring high efficiency and long-term durability. Models that consider heat and mass transfer can help designers understand how temperature gradients and water accumulation might affect performance. For instance, localized overheating could lead to membrane dehydration, while excessive water accumulation can flood the gas channels, both adversely affecting the fuel cell's operation. Mechanical integrity and stress analysis. PEM fuel cells often operate under varying pressure and temperature conditions, which can cause mechanical stresses in the components, potentially leading to failure. Stress analysis tools can model these mechanical aspects, identifying potential points of failure and helping in the design of more robust systems. These tools are particularly useful when selecting materials for bipolar plates and gas diffusion layers, as they need to withstand both mechanical stress and corrosive environments. Characterization techniques. Spectroscopic analysis for PFSA ionomers. The physical and chemical properties of perfluorosulfonic acid, PFSA, ionomers like Aquivian are critical for the performance of PEM fuel cells. Spectroscopic techniques such as Fourier transform infrared spectroscopy, FTIR, X-ray photoelectron spectroscopy, XPS, and nuclear magnetic resonance, NMR, are often used to characterize these ionomers. These methods provide insights into the chemical composition, molecular structure, and proton conduction pathways of the ionomers, thereby helping in selecting the most suitable type for specific applications. In situ and ex situ diagnostic methods. In situ diagnostic methods, such as electrochemical impedance spectroscopy, EIS, and current voltage, IV, curves, provide real-time data on the fuel cell's operational performance. These techniques are crucial for studying the dynamic behaviors, like activation losses or mass transport limitations, directly within the working fuel cell environment. Ex situ methods involve the study of individual components outside of the operational system. Techniques such as scanning electron microscopy, SEM, for electrode morphology, or thermogravimetric analysis, TGA, for thermal stability, offer insights into the material's properties and their suitability for long-term use in fuel cells. Characterization techniques play a vital role in understanding the intricate details of each component involved in PEM fuel cells. They provide essential information required for the optimization of the design and operation of fuel cells. Furthermore, the diagnostics can help correlate the properties of materials like PFSA ionomers to the overall cell performance, assisting researchers and engineers in their quest for more efficient and durable systems. Operational challenges. Water management. Water management within a PEM fuel cell is a delicate balancing act. While water is essential for maintaining the conductivity of the ionomer membrane, excessive water can lead to flooding in the cell, obstructing the gas channels and leading to performance degradation. Conversely, insufficient water can cause the membrane to dry out, diminishing its proton conducting ability and risking mechanical failure. Effective water management solutions like hydrophobic treatments for gas diffusion layers and proper channel design are crucial for optimal performance. Temperature control. PEM fuel cells generally operate at temperatures ranging from 50 to 100 degrees Celsius. Keeping the cell within this temperature window is critical for maximizing efficiency and lifespan. Temperature control systems, often comprising of heat exchangers and thermal insulating materials, are integrated into the fuel cell stack to manage heat generated during operation. Failure to control the temperature effectively can lead to accelerated degradation of the ionomer membrane and other cell components. Contaminant mitigation. Contaminants, especially in the hydrogen fuel or the air supply, can have severe adverse effects on the performance and durability of PEM cells. Even trace amounts of impurities like sulfur compounds or carbon monoxide can poison the catalyst, reducing its effectiveness. Filtration systems and purification steps must be rigorously designed and implemented to mitigate the risks associated with contaminants. Operational challenges in PEM fuel cells often arise from the complex interactions between various components and operational conditions. Addressing these challenges requires a multidisciplinary approach that combines materials science, fluid dynamics, thermal management, and chemical engineering. Overcoming these challenges is crucial for the broader commercialization and adoption of PEM fuel cells, particularly when powered by green hydrogen, a clean but demanding fuel in terms of purity and operational requirements. Market landscape. Companies specializing in PFSA ionomers. Several companies have specialized in the production of perfluorosulfonic acid, PFSA, ionomers, which are essential components of PEM fuel cells. Solvay, with its Aquivian series, is a significant player, but other companies like DuPont, known for Nafion, and 3M also offer competitive products. These companies focus on innovations to improve conductivity, thermal stability, and durability, which are critical factors for the success of PEM fuel cells. Intellectual property and patents. The market for PFSA ionomers and PEM fuel cells is dense with intellectual property, including patents on the ionomer structure, fuel cell stack design, and various system components. Companies frequently engage in R&D collaborations, licensing agreements, or acquisitions to secure valuable IP that can offer a competitive edge. Keeping abreast of patent landscapes is essential for both established players and new entrants to avoid litigation risks and to identify potential areas for innovation. Cost-benefit analysis for adopters. Adopting PEM fuel cell technology, particularly with high-performance PFSA ionomers, involves a considerable initial investment. However, the long-term benefits often outweigh the costs, especially in applications where low emissions and high efficiency are crucial. With the declining costs of green hydrogen production, the total cost of ownership for PEM fuel cell systems is increasingly becoming competitive with traditional energy systems. This trend amplifies the value proposition for adopters, from automotive manufacturers to stationary power providers. The market landscape for PEM fuel cells and PFSA ionomers is both complex and dynamic, influenced by technological advancements, regulatory frameworks, and the increasing demand for clean energy solutions. Understanding this landscape is critical for stakeholders ranging from material suppliers to end users, as it helps to identify opportunities and challenges in the ever-evolving quest for sustainable, efficient energy systems. Thank you for joining us for this in-depth look into the world of green hydrogen and PEM fuel cells. For more technical insights into renewable energy technologies, stay tuned to RenewEnergy.com. Thank you for choosing RenewEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at RenewEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.